Here is today's problem. We are presented with a system consisting of two equations. The first equation states that the variable x plus the variable y is equal to 4. The second equation states that x squared plus y squared is equal to 14. We want to find the exact values for x and y that satisfy both of these conditions simultaneously. To solve a system of equations with two variables, a standard and reliable approach is to use substitution. We begin by looking at the first equation, x plus y equals 4. Our goal is to isolate one of the variables so we can express it entirely in terms of the other variable. Let us isolate the variable y. To do this, we need to remove x from the left side of the equation. We accomplish this by subtracting x from both the left side and the right side. On the left side, we have x plus y, and we subtract x. The positive x and negative x cancel each other out exactly to 0, leaving only the variable y. On the right side of the equation, we had a 4, and we must subtract x from it, which gives us the expression for minus x. We have now established a direct relationship. We can state that y is exactly equal to the quantity 4 minus x. Now we turn our attention to the second equation in our system, which is x squared plus y squared equals 14. Since we just determined that y is equal to the quantity 4 minus x, we can substitute this expression into our second equation wherever the variable y appears. The first term of the equation is x squared. This term does not contain a y, so it remains exactly as it is. Next, we have an addition sign, followed by y squared. Here is where we make our substitution. We replace the variable y with the expression for minus x. Because the original equation squares the entire value of y, we must place our new expression for minus x inside parentheses and apply a square exponent to the entire group. Finally, the equation remains equal to 14 on the right side. Our new substituted equation is written as x squared plus the quantity 4 minus x squared equals 14. Notice that this equation now contains only a single variable, x. The next necessary step is to expand the squared binomial for minus x. Squaring a quantity means multiplying that quantity by itself. Therefore, we must multiply the binomial for minus x by another binomial for minus x. We will execute this multiplication using the distributive property, ensuring every term in the first binomial is multiplied by every term in the second binomial. We begin with the first term of the first group, the number 4. We multiply this 4 by the first term of the second group, which is also 4. The product of 4 and 4 is 16. Next, we multiply that same initial 4 by the second term in the second group, negative x. The product is minus 4x. Moving on, we multiply the second term of the first group, negative x, by the first term of the second group, positive 4. The product is another minus 4x. Finally, we multiply the second term of the first group, negative x, by the second term of the second group, which is also negative x. When we multiply a negative by a negative, the result is positive. Multiplying x by x yields positive x squared. We now have a series of 4 terms representing our expanded binomial. The terms are 16 minus 4x plus x squared. We can simplify this expression by combining the terms that are alike. The two terms in the middle, negative 4x and negative 4x, are like terms. When we combine them, starting at negative 4 and subtracting another 4, we arrive at negative 8. Therefore, those two terms merge into a single term of negative 8x. The other terms do not have any other like terms to combine with. Putting the pieces together, the completely expanded form of our squared binomial is 16 minus 8x plus x squared. We will now take this expanded form and substitute it back into our main equation in place of the parenthetical term. The original substituted equation began with an x squared. We write that x squared down first. Following that, we add the expanded form we just calculated. We add 16 minus 8x plus x squared, and all of this remains equal to 14 on the right side. Our updated equation reads x squared plus 16 minus 8x plus x squared equals 14. We must simplify the left side of this equation by once again combining like terms. Scanning the left side, we see an x squared term at the very beginning and another positive x squared term at the end. When we add one x squared to a second x squared, we obtain 2x squared. The remaining terms on the left side are the minus 8x and the positive 16. Neither of these has another like term on the left side. So, we rewrite the left side using our combined term. The left side is now 2x squared minus 8x plus 16. The entire equation is 2x squared minus 8x plus 16 equals 14. To solve a quadratic equation effectively, standard practice dictates that we move all terms to one side of the equation so that the other side is exactly equal to 0. To achieve a 0 on the right side, we must subtract 14. To keep the equation balanced, whatever we do to the right side, we must also do to the left side. So, we will subtract 14 from both sides of the equality. On the right side, 14 minus 14 is 0. On the left side, we locate the constant term, positive 16. We subtract 14 from 16, which is equal to a positive 2. The other terms on the left side, the 2x squared and the negative 8x, are unchanged because we are only subtracting a constant. Our newly balanced equation is 2x squared minus 8x plus 2 equals 0. We can simplify this quadratic equation further by inspecting the numerical coefficients. The coefficient on the x squared term is a positive 2. The coefficient on the x term is a negative 8. The constant term is a positive 2. The numbers 2, 8, and 2 are all even numbers, which means they share a common factor of 2. We can divide every single term in the equation, on both the left and right sides, by this common factor of 2. We start with the first term, 2x squared. Dividing 2x squared by 2 leaves us with a single x squared. We move to the second term, negative 8x. Dividing negative 8x by 2 gives us negative 4x. We move to the third term, the positive 2. Dividing 2 by 2 gives us exactly positive 1. Finally, on the right side, dividing 0 by 2 simply remains 0. Our final, simplified quadratic equation is x squared minus 4x plus 1 equals 0. This equation is written in the standard quadratic form, a times x squared plus b times x plus c equals 0. We will now identify the specific values for our variables a, b, and c to use in the quadratic formula. By looking at our equation, the x squared term has an implied coefficient of 1. Therefore, the value of a is equal to 1. The x term is preceded by a minus 4. Therefore, the value of b is equal to negative 4. The constant term at the end is a positive 1. Therefore, the value of c is equal to 1. We will utilize the quadratic formula to find the values of x. The quadratic formula dictates that x is equal to negative b, plus or minus the principal square root of the quantity b squared minus 4 times a times c, with that entire resulting expression divided by the quantity 2 times a. Let us carefully substitute our specific values of a, b, and c into this formula. The numerator begins with the negative of b. Because our b value is negative 4, the negative of negative 4 transforms into a positive 4. We write down 4. Following the 4 is the plus or minus symbol. Next is the square root symbol. We must construct the expression inside the square root. The first piece is b squared. We take negative 4 and square it. Negative 4 multiplied by negative 4 produces a positive 16. Next, we must subtract the product of 4, a, and c. We begin with a subtraction sign, followed by the number 4. We multiply this 4 by our value, 1. 4 times 1 remains 4. We then multiply that result by our c value, which is also 1. 4 times 1 still remains 4. The total amount we are subtracting is 4. The entire expression inside the square root is therefore 16 minus 4. Now we look at the denominator of our large fraction. The denominator is 2 multiplied by a. Since a is equal to 1, 2 times 1 is 2. We place a 2 in the denominator. The complete substituted formula reads, x is equal to 4, plus or minus the square root of the quantity 16 minus 4, all divided by 2. We evaluate the arithmetic inside the square root first. We have the quantity 16 minus 4. Subtracting 4 from 16 yields 12. The number 12 is positive, which confirms that our equation will yield real numbers for our solutions. We rewrite the formula with this result. X is equal to 4, plus or minus the square root of 12, all divided by 2. The next step is to simplify the square root of 12. To accomplish this, we search for the largest perfect square factor of the number 12. The integer factors of 12 are 1, 2, 3, 4, 6, and 12. Within that list, the number 4 is the largest perfect square. We can rewrite the number 12 as the product of 4 and 3. Therefore, the square root of 12 is exactly the same as the square root of the quantity 4 times 3. According to the properties of square root multiplication, we can split this into 2 separate radicals. It becomes the square root of 4 multiplied by the square root of 3. We know that the principal square root of 4 is exactly 2, so the expression simplifies to 2 multiplied by the square root of 3. We substitute this simplified radical back into our equation for x. Our equation is now x equals 4 plus or minus 2 times the square root of 3, all divided by 2. We can now simplify this fraction by dividing both terms in the numerator by the denominator. The numerator consists of the terms for and the term 2 times the square root of 3. The denominator is 2. We begin with the first term. 4 divided by 2 is exactly 2. We move to the second term. 2 times the square root of 3 divided by 2 leaves us with just the square root of 3, because the 2 in the numerator and the 2 in the denominator cancel out perfectly. Putting this together, our final simplified expression for x is 2 plus or minus the square root of 3. The plus or minus symbol indicates that there are 2 separate and distinct values for x that satisfy the quadratic equation. We must evaluate both paths. The first path uses the plus sign. This gives us our first value for x, which is x equals to plus the square root of 3. The second path uses the minus sign. This gives us our second value for x, which is x equals to minus the square root of 3. Finding the x values is only half of the requirement. For each specific x value, we must calculate its corresponding y value to form a complete solution pair. We return to the substitution equation we defined at the very beginning of our process. We establish that y is equal to 4 minus x. We will use this equation twice, once for each value of x. We begin with our first calculated x value, which is 2 plus the square root of 3. We substitute this entire quantity into the equation for y. The equation becomes y equals 4 minus the quantity 2 plus the square root of 3. It is absolutely crucial to place parentheses around the substituted quantity because the negative sign must distribute to every term inside. We apply the negative sign to the positive 2, making it a negative 2. We apply the negative sign to the positive square root of 3, making it a negative square root of 3. The expression for y is now 4 minus 2 minus the square root of 3. We combine the integer numbers. 4 minus 2 is exactly 2. The negative square root of 3 term remains unchanged. The final value is 2 minus the square root of 3. This completes our first pairing. When the variable x holds the value of 2 plus the square root of 3, the variable y must hold the corresponding value of 2 minus the square root of 3. Now we repeat the process for our second calculated x value. This second x value is 2 minus the square root of 3. We substitute this quantity into our y equation. The equation becomes y equals 4 minus the quantity 2 minus the square root of 3. Once again, we must distribute the negative sign to both terms inside the parentheses. The negative sign applied to the positive 2 creates a negative 2. The negative sign applied to the negative square root of 3 creates a positive square root of 3. The expression for y is now 4 minus 2 plus the square root of 3. We combine the integer components. 4 minus 2 is exactly 2. The positive square root of 3 term remains unchanged. The final value is 2 plus the square root of 3. This completes our second pairing. When the variable x holds the value of 2 minus the square root of 3, the variable y must hold the corresponding value of 2 plus the square root of 3. We have successfully identified 2 distinct solution pairs. The first complete solution is x equals to plus the square root of 3, and y equals to minus the square root of 3. The second complete solution is x equals to minus the square root of 3, and y equals to plus the square root of 3. To guarantee accuracy, we will verify both solution pairs by substituting them back into the original starting equations. We will begin by testing the first solution pair. We take x equals to plus the square root of 3 and y equals to minus the square root of 3. The first original equation is x plus y equals 4. We substitute our values. On the left side, we write our x value to plus the square root of 3, and to that we add our y value to minus the square root of 3. We gather the whole numbers together. 2 plus 2 is 4. Next we gather the radical terms. We have a positive square root of 3 and a negative square root of 3. When we add a value to its exact opposite, the result is 0. The square root terms cancel completely. We are left with exactly 4. This matches the right side of the first equation perfectly. Next, we test this same first solution pair against the second original equation, which is x squared plus y squared equals 14. We substitute our values to create the equation, the quantity 2 plus the square root of 3 squared, plus the quantity 2 minus the square root of 3 squared. We must calculate the square of the first binomial. We multiply 2 plus the square root of 3 by 2 plus the square root of 3. Using the distributive process, we multiply the first terms to get 4. We multiply the outer terms to get to square root of 3. We multiply the inner terms to get another to square root of 3. We multiply the last terms, square root of 3 times square root of 3, to get 3. We combine these parts. Adding the integers 4 and 3 gives 7. Adding the two radical terms gives positive 4 times the square root of 3. The first binomial squared results in 7 plus 4 times the square root of 3. Now we calculate the square of the second binomial. We multiply to minus the square root of 3 by to minus the square root of 3. The first terms multiply to 4. The outer terms multiply to negative to square root of 3. The inner terms multiply to another negative to square root of 3. The last terms multiply to positive 3. We combine these parts. Adding the integers 4 and 3 gives 7. Adding the two negative radical terms gives negative 4 times the square root of 3. The second binomial squared results in 7 minus 4 times the square root of 3. We bring these two expanded results together to finish the second equation check. We take the first result, 7 plus 4 times the square root of 3, and add the second result, 7 minus 4 times the square root of 3. We combine the integers. 7 plus 7 is 14. We combine the radical terms. Positive 4 times the square root of 3 added to negative 4 times the square root of 3 results in 0. The terms cancel completely. The final sum is exactly 14. This matches the right side of the second equation perfectly. The first solution pair is completely verified. Finally, we will verify the second solution pair. We take x equals to minus the square root of 3 and y equals to plus the square root of 3. We check it against the first equation, x plus y equals 4. We substitute our values. On the left side, we write our x value to minus the square root of 3, and to that we add our y value to plus the square root of 3. We gather the whole numbers. 2 plus 2 is 4. We gather the radical terms. We have a negative square root of 3 and a positive square root of 3. They cancel to 0. We are left with exactly 4. This perfectly matches the first equation. We now check the second pair against the second equation, x squared plus y squared equals 14. We substitute our values. We have the quantity to minus the square root of 3 squared, plus the quantity to plus the square root of 3 squared. Notice that this expression is composed of the exact same to squared binomials we just finished expanding in the previous check, simply presented in reverse order. We already know the results of these expansions. The square of to minus the square root of 3, 7 minus 4 times the square root of 3. The square of to plus the square root of 3, 7 plus 4 times the square root of 3. We add these two established results together. We take 7 minus 4 times the square root of 3, and add 7 plus 4 times the square root of 3. We combine the integers. 7 plus 7 is 14. We combine the radical terms. The negative 4 times the square root of 3 cancels exactly with the positive 4 times the square root of 3 to make 0. The final sum is exactly 14. This matches the right side of the second equation perfectly. Both pairs of calculated solutions independently satisfy both equations in the system. The procedure is complete. Thank you for watching. Please like and subscribe.